All right, today we want to look at the idea of a function in mathematics, and the title of this is Introduction to Functions. So obviously we're introducing something new here. And to do that, I have these two tables here with Luke and Han, and they have the distance that Luke traveled in a certain number of seconds. And this is something that we've kind of gotten used to here, listing things in a table. But the whole idea of a function in mathematics is a pretty important one, all right? Because if you look on your little note packet here, I have right below these tables what a function is. And we say that a function is like a rule, all right? A rule, or a lot of times we refer to a function or a rule as a formula, all right? And this is going to come really important in the next topic when we go into volume and such, but we'll get to that later. All right, so let's just talk about real quickly before we jump into the exercises here. What makes something a function and what makes something not a function? All right, so here let's look at the tables here with Luke and Han. And if I go over to Luke, we have a certain input. I'm going to put the word input right up here. Okay, and we have a certain output. And a lot of times when we're talking functions or we're talking formulas, we say that a function has a certain input, and every input yields or maps or gives a certain output. All right, and so let's test that. Let's see if each input yields a certain output. All right, with Luke's table over here. So if he goes 0.5 seconds, the distance he traveled is 4 feet, right? Okay, so if he goes 1 second, the distance he traveled is 16 feet. All right, so far each of these inputs are yielding only one output over here. Okay, so we go down the line and we match these up, and what I'm looking for is, are there any of these inputs that happen twice, happen more than once? All right. And if I look down the line, it looks like, well, no, that doesn't happen. Every one of these inputs are different over here. 1.5, 2, 2.5, 3, 3.54. I don't have another row down here. I'll write one in. I don't have another row that has a 4 and mapping to, say, a different number, like 296 over here. I don't have that. All right. In fact, we'll take that right back off. Okay. And that's what I want to look for if I want to determine if something is a function or not. All right. If it were the case where I had, say, a 4 and 296, that would mean the 4 as an input would map or would yield or would give a result of 2 different outputs, and that would be bad. That would make it not a function. All right. So let's look at Han over here. Han has an input over here of certain number of seconds, and he has an output, all right, of distance traveled. So again, if we go down the line, all right, let's see, 0.5 yields or maps to 4. Okay, well, that's all right. 1 second maps to 4 as well, but that's okay. All right, that is okay. It's okay if they repeat over here, okay? But now look at these right down here. I'll put a little star by both of these. This right here, this is what makes it not a function, because you have a 1, which is the same thing as this one, mapping to or yielding a different number. All right, so it's almost like you have 1 mapping to 4, and you also have 1 mapping to 36. All right. Now, it doesn't mean it's a bad thing. It just means that this is not a function right here. Okay? So I'm going to label this one. You go ahead and do that too. This is not a function. Okay? And if a a situation is a formula-based situation, then that is not going to happen. All right. I'm also going to put little stars down to the 3 down here. If you look ahead, 3 also maps to 2 different numbers. Okay. 3 maps to 99, and 3 maps to 196. So again, I'm going to write that over here too. 3 maps to 99, and it also maps or yields 196. Okay, so in order to be a function, we do not want that to happen. So this one is a function over here with Luke. This one is not a function over here with Han. All right. So let's go into the exercises now, and let's give these a shot. Let me switch over here, turn that off, and turn this one back on. Okay, and so exercise 1, simply yes or no, and we'll want to explain why. Why, if they represent a function or not. So here's what I do: I take each input and I see, does it map to an output? Well, they all do. Okay, but do I have the same input mapping to a different output? And right here, I'm going to circle these right here, this 5 and this 5, they're the same. And look, they're mapping to different outputs here. All right, so I'm going to put next to this one, no, that one is not a function. All right, and for a reason, I can put 5 maps to 19 and 20. All right, so it maps to 2 different outputs, so that is not good. Let's take a look at the second one down here. Let's see, 0.5 maps to a 1. All right, that's good. Now 7, you see it right here. Look at 7 maps to 15. I'm going to circle that one because I can see right here 7 also maps to 10. All right, so again, this is a no. This is not a function because 7 maps to 15 and 10. All right, so that makes it not a function. Let's see this one. I think this one is a function. If you look down the line here, once you do a few of these, they're pretty easy. Do you see any repetition here in the inputs? Well, you don't. You got 10, you have 20, 50, 75, and 90. So this one is a function. Yes, it is. And if you want a reason, you can say each input maps or yields or gives, whichever word you would like to say. I'm just using the word maps. Each input maps a specific, I shouldn't say it that way, I should say each input maps to only one output. Okay, let me say it that way. All right, so that's pretty easy. All right, especially when it's in a table like this. All right, we'll get to some eventually that will look like graphs, and we'll have little trick to determine if that's a function or not. So, all right, so that's pretty straightforward. Let's try number 2. Okay, well here is exercise 2, and this is why I like to call functions, a lot of times I call them formulas. All right, so this one says, given the equation d equals 8t squared, well, fill in the chart. All right, so firstly, fill in the chart. Well, that's pretty easy. They give us an input, and they tell us that this input, this is representing the variable t. All right, so all I have to do is to take each one of these numbers and plug them in for t. All right, these are nice, easy, what I call them plug and chug problems. You plug in the answer, or you plug in the value for the variable and just chug out the answer. So every place I see a t, I'm going to plug in a 2. And well, that's pretty easy. 2 squared. I follow my order of operations. 2 squared is 4. And then 8 times 4 is 32. Okay, so a 32, if I have an input of 2, I'm going to have an output of 32. All right, and I'm going to do that for each one of these. And I'm going to plug in a 4. So that's 8 times 16, which is a pretty big number. That's going to be, what is it, 108. Okay, so that's going to be 108. Now, I'm going to take a few minutes and just fill in the rest of these values. And you go ahead and do the same here. That's going to be 36. All right, we might have to get the calculator out for that one. All right, let me call up my calculator. Where is it? There it is. All right, here he is. My trusty calculator times 36. Whoops, hold on. 8 times 36. There we go, 288. All right, so that's 288. Put it down there as well. Okay, and let's see. Again, just plug in. See, I'm using the same formula every time, the same function every time. Well, I don't know if it's a function yet. We're going to determine that. All right, but anyway, this is 8 times 64. And I'm going to go ahead and fill these in and then call up my calculator and figure them out. Oh, this one's pretty easy. That's 8 times 100. So that's 800. Okay, so I know this one's 800. I get out the calculator for this other one. Let's see, 8 times 64. Oh, that gives me 512. Okay, I'll get rid of that guy. So that is 512. And there you go. Okay, so fill in the chart. Boy, that's something that's pretty easy. You just use this equation every time and plug in whatever value they have for the input. All right, now the key is, what is it? Is it a function or not? All right, and this is the same thing we just got done doing here in the previous example. We take each one of the inputs, and every input that we have should only map to one specific output. All right, so it looks like the 2 is mapping to 32, and 4 is mapping to 108, okay, and 6 is mapping to 288, etc., etc., okay, and it looks like yes, this is a function. Now be careful, all right, be careful, because it depends on the inputs that they give you. If I were to give you, I want to show you this real quick. What if we were to use an input of -10? Okay, what if we were to use a -10? All right, I know this is not one of the inputs they gave us, but just by these inputs, yes, it is a function. But if I were to use, all right, if I were to use -10, some people may say, wait a minute, when I plug in -10, I'm going to put a negative, okay, put a negative sign right there. Okay, what do I get? I get -10 squared. Remember, negative times negative is a positive, and I get 800. So, if I had a -10 out here, I would also get 800. All right, now, question is, would that make it still a function? And some people would say, oh, wait a minute, I got these to repeat. It's not a function. But remember, it's okay, all right? As long as you have a different input they can lead to the same output. That's okay. This is still a function, all right? I just want to put that up there, all right? So yes, this is a function. Even if I put in some other inputs, it's still going to be a function. So, all right? So that's pretty straightforward there. Pretty straightforward. Put in the table there and determine as a function. Let's try something else. Let me turn off that one. Switch over to this one. Okay. And let me erase this guy. He kind of hanging out there. Oh, I can't erase that guy. Let me try it this way. Erase this guy like this, maybe. Let me take this guy out of there. All right, and turn him off. There we go. Okay, we got rid of it. So, all right, so let's try this one. It takes Josephine 34 minutes. Notice each one of these problems, we're kind of stepping it up a notch here. So it takes Josephine 34 minutes to complete her homework assignment of 10 problems, okay? If we assume that she works with a constant rate, okay, we've seen this before, constant rate. All right, that reminds me of the word slope. Okay, so we can describe the situation using a function. All right, so here's what we want to do. First, we want to step through this here. It says predict how many problems Josephine can complete in 25 minutes. All right, well, we've done this for a while now. We can set up a proportion All right, we can set up a proportion to figure out how many problems she can do in 25 minutes. So let's make this into a rate, or again, I'm thinking in the back of my mind slope. All right, because I know what's coming next here. So it takes her 34 minutes to do 10 problems. So I'm going to write that as a rate, 10 problems in 34 minutes. Usually we put the time variable or the time unit on the bottom, right? So we're gonna make a proportion, and we're going to equate that to, well, they gave me 25 minutes, and they want to know what x is. How many problems can she do? All right, and we all know how to solve that proportion. We cross multiply, so 25 times 10 is 250, and 34 times x is 34x. And it looks like I'm going to have to bring up my calculator again. All right, here he is. And because I'm going to divide both of these by 34, okay, and that's going to give me a value for x. So I take 250, and I divide by 34, and that is 7 point, I'm going to round to the nearest tenth. Actually, it's problems. Well, how many problems could she get done? So I'm going to go to the whole number here, and I'm going to round to be 7. Actually, I'm not really rounding. I'm knocking off the decimal there because 0.4 of a problem, that really doesn't make sense. So she can do 7 problems there. All right. So x equals 7. All right. Now it says write a two-variable linear equation. All right. We should remember that. That should remind us that we should use y equals mx plus b. All right. Whenever you have a linear equation, you have the general form y equals mx plus b. So I'm going to go over here to do that, and our slope is right here. Here's her constant rate. Okay, her slope is going to be 10 over 34. 10 over 34. Oh, that's pretty bad. We're going to make that a little better. Okay, and x still stays right where it is, but I need my y-intercept. Okay, well now let's think about this. If this is the time taken to complete problems, and this is the number of problems she completed, well, remember the y-intercept is always where x equals 0. All right, so if she takes 0 time, okay, she's going to have 0 problems done, right? Okay, so her y-intercept here really is just 0. Okay, so her whole equation, the two-variable linear equation, is 10 over 34 x. I don't have to write that 0 here, so here it is. Here's her constant rate as the slope, and her y-intercept, if she takes 0 time to do anything, she's going to have 0 problems done. All right? Okay, so the last part here, it says use the equation wrote in part B, so that would be this one right here, as a formula or a function to complete the table below. So we want to know, what if she takes 10 minutes? Well, then once you have this formula, this is why functions are so great. Once you have this formula, it's really plug and chug. All right, plug the numbers in and chug out the answers. So if she takes 10 minutes, so we're going to plug in 34, and we're going to plug in a 10 right there. Okay, and if she takes 15 minutes, we're going to plug in this formula or this function. We're going to plug in a 15. All right, now I'm going to pause my video, and you guys go ahead and try to fill the rest of these in. I'm going to fill them in, and we'll hopefully get the same answers. Okay, so I plugged in the input into each into this formula, all right, for each of them, and here are the answers that I got. Notice it says to round to the hundredths place in these problems. All right, so I did that, and that, like I said, is just plug and chug problems. Plug them in for x and figure out what the answer is. Just multiply by 10 over 34. All right, so that shouldn't be pretty hard. Okay, and this very last part, it says use the formula from above to compute the number of problems completed when x equals -7. All right. And it also says, does this answer make sense? Well, when x equals -7, all right, let's plug in a -7 there. So all I have to do is multiply these two numbers together. So 10 times a -7. Let's see. 7, we're going to make that negative, equals that. And we're going to divide by 34. All right. Oh, I get -2.06. Okay, and now does that answer make sense? Look at what y stands for here. Y is the number of problems together. Does it really make sense that she completed a negative number of problems? And no, that does not make sense. You cannot go backwards in the number of problems that you completed. You can't complete a negative amount of problems. All right? All right, so there's a little introduction to functions for you. When you do the assignment that goes along with this video, they will be very similar to what we've done here. All right, so have a good night. Thanks for watching. Catch you later.